Okay, so now this is the question on hand. Question. How do we determine the intervals or intervals where a function is concave up and same question where a function is concave down. Now, let's focus on the one where it's concave up. Okay, and let's look at this function once again. Let me rewrite the function. F of x was x squared plus 1, and f prime of x was 2x, and f double prime of x is 2. Now, what did we say once again here? For when a function is concave up, right, it appears that what? The slope of the tangent line as you go from left to right, it's very negative, still negative, but less negative, goes to 0, and then what? Becomes positive and becomes very positive. Now, what did you say once again? The second derivative is the rate of change of the first derivative. And what do we observe? As you go from left to right, the second derivative is positive, which means what? So that means that the derivative is increasing as a function. Now, what I want you to do at home is when you draw f of x equal to x squared plus 1, I want you to actually draw the graph of f prime of x on the same xy plane. Actually, let's do that. And then I want you to do it for g of x. So what do we observe here? We have the line 2x. So this will end up being the derivative. And then, when we look at the second derivative, to be a straight horizontal line, so this is your f double prime of x, which is equal to 2. So what I want you to do at home is to do the similar thing to g of x. But what do we observe here? Okay, we observe that when the second derivative is positive, the function is concave up. So we're going to put that as what we will call as our test for concavity. We say what? The following. If the second derivative of a function is positive on open interval from a to b, then we say that f of x is concave up on that interval from a to b. In a similar fashion, in a different fashion, when we now look at when the second derivative of a function is negative, on an interval a to b, then we say that the function f of x is concave down on the interval from A to B. Now, what does this kind of tell us? Well, we notice that, it seems like once we have the second derivative of a function, right, and then we have a value c, such that what? Such that maybe to the left of c, let's just say the second derivative is negative. And let's say on the other side here, the second derivative is positive, meaning at C, there is a change in concavity. Well, we have a definition for this C. We say that f of x has an inflection point. Now, this is a point. That's why we have to say the point with coordinates c and f of c. Right? As an inflection point at that point, if f of x changes concavity at c. Now, keep in mind that we're basically assuming that the function has to be defined at c. In other words, we want the function to really be continuous at c. But what we would like to observe is, as you go from to the left of c, we have a change in concavity, meaning we have a second derivative to be negative, then positive, or the other way around. Okay, so what I want to do, I want to look at some of the examples that we have already looked at last Monday and try to find these intervals for concavity. So once again, I'll give you a chance to copy notes and ask questions.